Hello everyone, I'm Nathan, otherwise known as Old Man Bills, and I'm here with Todd Desiato, and we're going to go over his paper today. Todd, you want to say anything to everyone?
Hey everyone, I'm here to go over a paper I just released, an engineering model of quantum gravity, and it's a tool for you guys to engineer with. It's what you've been waiting for, I hope. So anyway, I'm an engineer. I've been doing power electronics for 40 years. I've got a associate degree in engineering physics from the County College of Morris, and then I got a Bachelor of Science in engineering physics from the University of California. So, and I've been working on understanding gravity through quantum electrodynamics for decades. And since the late 80s, early 90s, I was working on this. And what I've done with this paper is show that you can get gravitational time dilation and length contraction without general relativity just using quantum electrodynamics. So
Very good. Let's go ahead and bring up your paper here, Todd, so we can take a look at it. I got it in big size so I can read it on this thing. Okay.
Good.
An engineering model of quantum gravity, gravitational time dilation, and length contraction of radiative damping in quantum electrodynamics with general relativity.
Without
that's a mouthful.
Without general relativity. That's the catch.
I love it. So let's go over the experiment a little bit in the way you propose it. So we have an aluminum rod, right? So does any size will work, or just a couple inches, or
an example? Yeah.
Okay.
Thin aluminum rod. I'm just hypothesizing here.
So we put it in a vacuum chamber, and then what kind of energy do we put on it?
What is proposed in the work is using electron parametric resonance, EPR, also known as electron spin resonance, and at a frequency of 4.18 gigahertz, which would match in terms the Landau-Lifshitz damping frequency equivalent to the gravitational potential of the Earth. And if you read the paper, that would make sense. Yes. But in any case, the idea is that you're bombarding the rod so that every atom in the rod is vibrating or oscillating at this frequency. And then you create a very tiny frequency gradient, and the rod will move toward lower energy where the frequency is lower. And it will do this gravitationally, just like a free-falling body.
Okay, so let me just remove this real quick. So what we're doing is we're putting the microwave energy in it basically at that level, right?
Yeah.
So then we're creating a field that goes around it, and the atoms swirl around that field, right?
Yeah, basically they precess like a spinning top.
Okay. Yeah, I remember watching that with the right hand rules positive, left hand rules negative, right?
Yep.
Okay. So, okay. Now with that, you're able to tell exactly how much gravity is in something in comparison to the Earth?
No, not that way. It's that if you look at the paper on page, which one? Page 7? No. Page 6. There you go. Passed it.
There we are. Okay.
I think you passed it.
Down?
Yeah, that's it. Right there. Right there. Right there. Equilibrium spacing. So, okay, take it down a little more.
A little more?
More. Oh, it kind of goes into the next page. I see it's 6 and 7. On my screen, it's all 1. So.
Oh, gotcha.
Yeah, I got it. What you have here is a frequency equation where the damped angular frequency is the natural angular frequency times the square root of 1 minus the square of the Landau-Lifshitz damping factor, damping coefficient, divided by 2 times the natural frequency, that quantity squared. And then we approximate it to make it simpler to work with. And now if you scroll down to equation 38 and 39, you see here, this would be in the same approximation in a gravitational well. You could replace m with the mass of the Earth and r with the radius of the Earth to the surface. So these two we equate. So gm over rc squared is equal to 1/2 gamma naught over 2 omega naught squared. And by doing that, we calculate the effective Landau-Lifshitz damping factor that equates to gravity for the Earth. And if you scroll down, you'll see the result.
There it is, therefore.
Yeah, and you get the damping causes the rod to contract. So instead of just having the spacing be determined by the derivative of the potential with respect to the spacing, you have this other term determined by the 0-point field and damping. And the 0-point field is like a source of energy that, if left alone in far from matter, like far out at the edge of the universe where there's no matter to cause damping, the rod would expand to its maximum length due to the 0-point field, energizing it. When we have mass nearby, like the Earth causes damping, and damping causes the rod to shrink. And that's what gravitational length contraction is about. But not only does it cause length to shrink, the length of the rod to shrink, as I showed back on equations 36 and 37, it causes the frequency of the atoms to decrease, which is equivalent and indistinguishable from gravitational time dilation. So here we have the two foundation rocks of gravity, gravitational time dilation and length contraction, come out of this math, which only uses radiative damping and quantum electrodynamics, not general relativity. So if we can, as engineers, design ways of causing damping, we can make artificial gravity. Or if we can find a way to amplify the 0-point field and keep everything in tune, we can cause rulers to expand, clocks to run fast, and we have what we need for warp drive. So these are, because warp drive is the opposite of gravity. It's anti-gravity. It's clocks run faster, rulers expand. Gravity is clocks run slower, rulers contract. If you want to go faster than light, you need to stretch the ship, race the clock, and then you'll actually get there faster than light.
So let me ask you this. When you're talking about stretching the aluminum or stretching the ship, is it physically or is it more in like a hypothetical sense? Is it physically you're like Play-Doh, you're pulling it apart and it's stretching?
Yeah, but if you're doing it right, it's not pulling it apart, it's just scaling.
Okay. Gotcha. Okay. Well, that's interesting. That's the first time I've ever heard that.
Well, if you think about it, we know of gravitational length contraction and time dilation. It's been measured, we use those in our calculations for the GPS system. But if you ever think about it, if you're lifting a ruler up against the force of gravity, the opposite is happening. That ruler is getting longer, and the clock you lifting up is getting faster. So anti-gravity, the opposite of gravity, is those two effects. And warp drive is the effect of we want to stretch the ruler so that the space between point A and point B is smaller in the frame of the ruler. Right? Now, everybody talks about space-time changing, for warp drive and stuff. But what are you really talking about? If space-time stretches and my ruler stays the same, doesn't that seem the same thing as if my ruler shrank?
Yeah, I guess that would make sense.
Relationship. When you're looking at it with fixed rulers and clocks, then space and time have to change geometry. That's the way general relativity is viewed. But for quantum gravity, you can't, pardon my French, but you can't freaking quantize empty space. There's nothing there, and the fields that are in it are already quantized. It's redundant. You're doing it twice. What matters in quantum gravity is how those fields interact with matter.
Interesting.
And it's the old saying is gravity, matter tells space-time how to curve, and space-time tells matter how to move. Well, everybody looking at these problems for gravity and anti-gravity keep wanting to change how space-time curves instead of just trying to make the matter move.
Yes, I've seen that. They always try to change the space-time in there.
Yeah, everything's about changing the space-time, which is essentially a stage which is filled with fields. It has no geometry of its own. Instead of saying, I'm going to control the scale of my rulers and clocks. How fast do they measure time? How long are how long or short is my ruler? And with these variable ruler and clock, I can go measure my fields and my geometry, knowing that it's the rulers and clocks that are changing, not the stage.
So does time play a factor in when you stretch it, right? And then when it bounces back to its original state once you get there?
Yeah. When you stretch it, your atoms are going to be running faster because the 0 point energy that's driving it is higher. And so its volume and length will expand. And each atom is its own clock, and it's oscillating at a higher frequency. And this is very cool, man. You're going to like this.
Okay.
That's what you need to overcome length contraction. So let's say we want to go to warp speed and we turn on our engine and we accelerate. Well, special relativity would tell us that we can't go faster than light. But in general relativity, what it says is that when we accelerate our ship, we're doing work that is compressing it. It's causing stress and tension, but it's compression on the ship. And all the atoms are slowing down and contracting and getting closer together. If you now have this effect that you can increase the 0 point field contribution and drive the atoms to oscillate faster and stretch back out to normal, then the rules of special relativity that you can't go faster than light no longer apply. You're basically back to Newtonian physics, but with a field that controls the oscillation frequency and separation distance between every atom.
Gotcha. Now I see where you're going with it. Okay. That makes a lot more sense.
Now here's the fun part. When you increase the energy contributed by the 0 point field and the rod or the ship expands and it scales and it gets larger, its volume increases faster than the energy you put into it, which means its energy density goes down.
So it moves faster.
Right. But what is exotic matter? negative energy density. So if I have a ship with positive energy density and I inflate it like this to a higher volume, larger volume, higher energy state, I've reduced its energy density. It is the equivalent mathematically of adding negative energy density to the ship.
That makes a lot more sense to have
All
the
right.
negative
Now
energy.
now you know what exotic matter is. This is what exotic matter is. It's using a higher amplified 0-point field to cause the ruler to stretch and the clock to run faster. And the volume expands faster than the energy you put in, thereby reducing the energy density. Whereas if you just tried to have a rocket and accelerate to the speed of light, it keeps compressing and the energy density keeps going up and you can never get there.
Right. You have too much pushing upon it at one time, and you need to lessen that amount.
Uh-huh.
That's better. So the field makes sense, and then you go faster, but you don't get the negative side. And I don't want to say negative, that's the wrong word. You don't get the inertia side of it, do you?
No. In fact, the two things you do get out of it is that when the ship is inflated to this, I call it inflated matter, and once it's inflated to this higher energy state, it's harder relative to us. So it's like its own shield, because matter in that state has a much higher energy. So it can deflect, whatever you want. And also the side effect of the field would be is any matter entering the field from outside, from like in front, would have a tendency to lose inertia and stretch out and just pass on by without causing any damage. It would also most likely be deflected because a warp drive, remember I said if you have to lift something to a higher gravitational field, if you're lifting the ruler up, it's getting longer. So an anti-gravity field, you have to do work to climb it. So incoming matter coming into this warp field has to do work to climb it. So the incoming matter is like going uphill, and it's going to slow down.
Yeah.
It's the ship. So it's got its own force field.
So we see when they do the rockets and stuff, there's a barrier that builds up in front of it. You know what I mean?
Shockwave. Yeah.
Yeah. So it slows it down.
Yeah,
so,
it does. I mean, yeah, if you've got stuff hitting you from the front, shield or no shield, it's going to slow you down.
Okay.
But it's not going to blow you up.
Yeah. I have a question about rotation. Now, and I don't know if this is the second part or the first part of your paper, but I wanted to ask you about the rotation. So if the field rotates, would it then displace the amount of energy pushed against it if you're in Earth's atmosphere going up?
I'm not sure I follow you.
So basically, we go against the barrier, like with our planes, right? And stuff like that. And then finally we break through the barrier, right? So if I spun this thing, okay, and we're talking about the field here, not the actual object, right? If I spun the field, can I get past this and get through, or is it still going to hit that field?
It depends on the symmetry. You can devise it with gaps. You can engineer anything, man.
Well, I like to ask the question only because I want to know if on the ground can we eliminate the inertia while we're in Earth, inside Earth? Because I know we're talking about space.
That's what I'm working on, is stuff that I can make work on Earth, because trying to do it in space is not something I have the capability of testing. Mark Sokol at Falcon Space has built a marvelous vacuum chamber now with an enormous vacuum, well beyond what is needed to test things. So we're all working on experiments that we can put in that machine next month.
Oh, really? How big is the machine?
Oh, it's like 14-inch diameter, and I think it's like 28 inches tall or something like that.
Hmm.
It's not huge, but it's very, very efficient at pulling a vacuum. So you get a very hard vacuum.
Oh,
Space.
I'd love for you to take your gravity flyer that you have and put it in there, Todd, and then put the fields on it.
The Graviflyer is too big, but yeah, we're working on other stuff
to make something smaller.
Dude,
well,
you're wasting your time with that.
I don't think so, but that difference in opinion. Last time you talked to me, you told me to put a hot air balloon to it.
That would work. Well, I'm trying to figure out ways to conserve, that it can fly and conserve momentum. The only other thing that you can, obviously, electromagnetic fields are not going to thrust that thing up. It's just not going to happen. You don't have gigawatts of power to drive it.
Oh, I don't need those fields. I just need it to contain the negative energy field that I'm pulling into it. You see, you think I didn't think of this.
If you can increase the air velocity coming out and direct it more downward.
I don't need to direct air velocity.
But there's no way to electromagnetically make that thing lift. It just won't do it.
I don't know. We're going to have to see. All right, let's get back to your paper, Todd.
I honestly think Alexei pulled off the greatest scam in history. But
well, we'll have to see, won't we? I've had positive results so far, and I'm going to keep going.
Okay.
So let's go on with your paper here, Todd.
Yep.
So I don't want to get too far off subject with you. Let's see.
So I did. Go ahead.
No,
I was I did some justification for this as an approximation, and the small damping approximation I used to get this equation is valid to objects, that are within two orders of a black hole. So things on Earth and gravity, the way we know it, my equations here, my equalities between gravity and damping are spot on. I mean, you can't deny it. The small damping approximation is well within the limits of gravity that we experience here on Earth. And it doesn't start to break down. The interpretation doesn't really start to break down until you try to cross the event horizon. Then all bets are off, because nobody knows what's on the other side of the event horizon anyway. It could be geometrical. It could be nothing. It could be everything stops on the event horizon, because that's the way we see it, and that's all we'll ever see.
Very cool. Okay. Let's see. Right here. Equivalence and a strong dampening limit. So, when we talk about the dampening in this, okay, you talk about, it says in there, it would take a black hole event horizon and be viewed by distant observer. The angular frequency becomes imaginary when my mouse clicked over it. By over dampening, and that's where the analogy breaks down. Okay.
Yep.
Go ahead. What is that?
Yeah, so let's say you've got a clock, and that's your frequency. That's your angular frequency. Whatever it is, it's an atom, it's a clock. It's falling into a black hole. From our perspective, looking at it from far away, the clock just keeps running slower and slower and slower until it gets to the event horizon, and then it stops. And from our perspective, from far away, it'll stay there forever.
Okay.
All right. But in reality, if it falls through that level, it will eventually, lose all energy, because it's going to it not only stop, all the atoms stop oscillating, and that's why it says it becomes imaginary. This is pretty much the same thing in relativity. If you cross the event horizon, then Schwarzschild's solution becomes imaginary. Same thing.
Okay.
Yeah.
I want to make sure I wasn't reading something
Yeah,
It
no.
was wrong.
Finkelstein came up with his own coordinates that don't do that, and I don't have the equivalent for that here. But it's a matter of interpretation. Is it geometry or is it rulers and clocks?
Well, I would say it's geometry. I see far too little of that in your guys' physics equations. So it always worries me because every time I see space time, it's on a flat plane going into a hole, and I never see it like the geometry of the Earth. You know what I mean? The sphere in there, and then
Well, here you go. That's the sphere. That's it. 2gm over r. That's the gravitational field of a sphere.
very good then. Okay, all right. So what we're looking at here, let me see. We're almost at the end of this right here. I want to look at the. If there's something you want me to stop on, let me know.
No, that's the number I mentioned before. 4.18 gigahertz is the equivalent number you get when you that calculation is basically deriving that number by equating the damping. And what you're showing right there is that the damping factor is 2 omega naught times the square root of 2gm over rc squared. And it comes out to 4.18 gigahertz. So if I use the mass and radius of the Earth. So that's the frequency we want to use for our nuclear and electron resonance, spin resonance. Is that meaningful? I do not know. This is the experiment. I don't know if that's going to work to induce damping at that level or not. But, it's that's the calculation you get. If somebody knows how to create damping at that level and then create a gradient in that damping, then you've solved the problem. So engineers, get with it. Get with the picture. Stop trying to curve space-time and figure out how to make this work.
That's a big number, Todd. 4.18 gigahertz, but then you got to multiply by
terahertz. It's not terahertz. It's not Planck length or Planck, Planck energy. It's small compared to all of that. This is actually in a range that can be engineered.
Okay.
Planck energies and Planck lengths and stuff like that. Engineers can't do nothing with it. We can't touch that stuff. This we can work with.
Always. Okay. That seems like a lot. I've gotten Tesla coils, or somebody else has, I should say, who's gotten close to gigahertz, but not that much. Not even.
Mark has a RF amplifier that does it. He's got.
Does he really?
Yeah. He's got several. He's got X band. He's got 9 gigahertz. I think the 9 gigahertz one fried.
What was he doing to it?
Oh, we're
just pushing it.
An Alzaphon experiment, which is basically weighing samples that are being bombarded by microwaves in a magnetic field to cause electron spin resonance. And if you got a gradient in that magnetic field, you're going to cause it to lose weight. And that's the idea. And that's kind of that last section in the conclusions there where you skip past it. That's the real thing that Mark and I are working on. So Mark's almost there. The thing is, anytime you got to have working those kind of frequencies, it's not a wire, it's not a cable, it's a waveguide, and then you got to polish your waveguide and get all your couplers sealed and everything's got to be perfectly square. And, and then the string you use to hold the sample melts from the microwave. So it's like, it's one thing after another. It's not an easy thing to do by any means, but now we have some equipment that's new for us, that's much more suited to doing nuclear magnetic resonance and electron spin resonance. So he's putting it all together, and we're hopeful we can get some positive results with this as a first step. But engineers, this is it. This is the approximation you need to engineer stuff to mimic or control gravity. Be my guest. I'd love to see it happen in my lifetime.
I would as well. let's see. Okay. So the second part deals with the Earth itself and the frequencies at heights. So do you want to get into that a little bit?
Yeah, it's simply that equation we're at the end there where we were just talking about the 4.18 gigahertz.
Right.
In this paper, I used that equation and created a table that if you show the table,
Okay.
it's real straightforward. I just run the calculation
Right
and
here.
boom. Yeah. So this is from sea level, 0 altitude, up to 10,000 meters. And you see here, gravity at the surface of the Earth is 9.798 where I'm at. If you're, where it located it, and then it gets a little less at 10,000 meters. And you see here the frequency at the surface of the Earth we got was 4.18 gigahertz. But if you're up 10,000 meters, it's only 4.1768 gigahertz. Tiny change, And
Yeah.
if you wanted to have a gravitational field that matches this acceleration in the frequency, then it's really only changing by about 327 hertz per meter. So you got this huge frequency, 4.18 gigahertz, but to induce a gravitational field, you only need to change it by 327 hertz per meter, and you'll have a 1G field.
Hmm.
You follow me?
Yeah, I'm following. So that's the change rate right there, the 327, right?
Caused by little g, or 9, by this acceleration. We have the surface of the Earth, and at this altitude, it's this. At a higher altitude, g is a little smaller, so the frequency gradient is a little smaller. But at the surface of the Earth, it's 327. At 10,000 meters up, it's 326. So it doesn't change much. It's fairly constant. And yeah, if we can cause a gradient in that frequency, we have a gravitational field. But the gradient and the frequency must be affecting all the atoms in the sample. And that's why we want to work with nuclear magnetic resonance, and so that all the atoms in the sample are precessing together at that frequency, and then they're going to want to walk down the gradient to a lower energy, to a lower frequency.
Okay, so you basically have to purge the sample to make it clean of all the the ones that don't work.
In this stage of this experiment, yes, but I mean, gravity doesn't do that. We need it to work with everything.
So I have another question for you. How thick does this field have to be in order to pressurize and be what you need it to do? Or does it have to be thick at all?
Like I say, if we use a thin aluminum rod, it only needs to be the size of the rod, because only the field that's intersecting the rod matters.
Okay, so if I had a ship on the ground instead of the rod, okay, now I have to resonate that entire ship at that frequency in order to get it to lift.
Mm-hmm.
So
with the frequency gradient of positive 327 hertz per meter.
So what does that do to the person inside, though? I mean, isn't he dead?
Nothing.
Okay.
Why would it?
Once you put in that kind of a frequency into something, doesn't it just start to burn things?
Too much, yeah. But I don't want to concentrate it on one atom or one spot. I want it to spread out and fill the entire volume.
Okay. And is it pulse, so it has a chance to cool down?
That's kind of the leading edge, man, because I don't know. I don't know the best way to do this. And, a pulse, an impulse, has a very wide bandwidth. So maybe that's kind of what we need is an impulse that can give us a wide bandwidth that can interact with all the atoms, not just aluminum. Right? And so if we have an impulse that has a very wide bandwidth and a frequency gradient, maybe it'll exert gravity. One of the things I wanted to test, and I couldn't get it, is I wanted to get these supercapacitor banks that have ultra low inductance, and ultra low series resistance, and charge it up and then discharge it into a impulse, like a gigawatt, several gigawatt wham, like a lightning bolt.
I want to see that.
And then measure how much gravitational interaction we get from that. Because the amount of power that's concentrated in one spot, it would have a very wide bandwidth and a very strong amplitude gradient anyway, if not a frequency gradient.
That would be highly destructive, Todd. You're acting like me now.
Use tungsten; it won't hurt nothing. Bang!
Yeah, you're just gonna do some welding on the weekend.
We gotta get a metal box that gets bigger on one end than the other end, so that we create a frequency gradient.
Okay.
And hit it like a speaker with a big spark gap on one end, and it should project the gravity wave out the other end.
Oh, I'm not standing next to that thing, Todd. That sounds really dangerous.
Neither would I. But, a vortex cannon, but for electromagnetism.
Oh, that's so great. Oh,
I love vortex cannons, man. They're awesome. So, yeah, I mean, it's a matter of modeling and engineering a gamma factor, a gamma LL, Landau-Lifshitz damping coefficient. We need to engineer that to get our gravitational fields. And so there are a lot of papers out there on Landau-Lifshitz damping. I didn't use any of them.
okay.
But there is a ton of research to be done in this field, because a lot of people know about Landau-Lifshitz damping, and they know how to make it and do it, and they're totally unaware of this. So if we can get some of those people on board who have worked with this before, that would be a big help.
Well, it'd be nice to see their studies and their paperwork behind it on, for how they scaled their stuff, so that you can see which direction you have to go in.
Yep. Anything, anyone who wants to help, we're open. We're open source. We're open to help. But I mean, as far as I'm concerned, if you want a first approximation to gravity and anti-gravity, this is it. This is something engineers can use. I've shown you how it works, why it works, and it's not wrong. Jack might say it's wrong, but Jack says everything is wrong if he didn't come up with it.
That guy keeps calling me a schmuck every time I watch it.
Yeah.
It's like every other word out of his mouth is that.
Say, I know you are, but what am I? It's projecting,
Oh, it's kind of hard to listen to after a while. He shows his credentials as soon as he walks in the door.
Jeremy invited me in when Jack was on. I was like, no way.
Yeah.
I don't need the aggravation.
Oh, I tried to watch it last time, and Jeremy was bringing up the weather. And I'm like, why do I care about the weather? Todd's on. I want to see what he had to say, because it's when you first came out with your paper, right?
Yeah, and he didn't really talk about it at all. It was just his show that day was about the stuff like, some members of the House GOP were saying, that the Dems are controlling hurricanes. And I'm like, do you know how many millions of square miles there are under a hurricane?
Hold on. The Democrats are controlling hurricanes? Is that
what you said? These people don't believe in climate change because man can't do that, but yet they believe that Democrats are controlling the weather. It's like my head hurts.
Oh, come on. I I know you Democrats out there. You guys control stuff, but not the weather. There's no way.
Not the weather. No.
No.
Even if we had every plane in the country circling that hurricane trying to seed it, it wouldn't help. It wouldn't do nothing. It's like blowing into the wind and thinking you're going to cause a tornado.
Oh, that's so funny. Oh, that's a conspiracy theory right there for you. That's a good one. Yeah, they were up there just controlling the weather. Why?
Congresswoman Green, man, she'll believe anything except the truth.
So now you have a technique to find the actual anti-gravity is what you're going with here. And we're going to have to get to gigahertz, okay, multiplied by 10 to the, was it 19th power or something? Nine power. Okay. There's still a lot.
Still a lot. Yeah.
And we're going to try not to die next to your lightning bolt over there with all of your capacitors. Oh, no, I think it's awesome, Todd, that you guys are looking into anti-gravity and working on it and trying to find a medium to work in. You know what I mean?
Yeah, it's hard because for my whole life, it's been like general relativity is bending space-time. And I'm like, you need planets to do that. How do I engineer with that? I mean, even the mathematics is daunting. But with this, I'm just using a scalar model of gravity. It's no less accurate than Newton's gravity for stuff we want to do on the surface of the Earth and beyond even. So unless we want to manufacture black holes, this is all you need. So I really would like to see more people start to think in terms of damping instead of general relativity, just because, not that I have anything against general relativity. I'm just offering a different way of looking at the same stuff because the equations match. The only difference here is the interpretation of what's going on. And if it's just a matter of interpretation, then who cares? Just make it work.
Yeah. Well, I tend to think on a different side than you. So negative energy. What is your opinion of it? Like, you mentioned it, but I think you mentioned it as a coefficient to the positive. So what is it you believe in?
Negative energy itself is an antimatter. That's negative energy. It's not what you need for warp drive. Warp drive requires negative energy density. That's exotic matter, not antimatter.
Okay.
It's a different animal. Antimatter has negative energy, but it has positive energy density. We need negative energy density. It's a different animal. And like I explained earlier, the way I've learned to interpret negative energy density based on how warp drive works in the model of gravity I'm using is that by amplifying the 0-point field and driving matter to inflate, I call it, instead of exotic matter, I call it inflated matter or inflatable matter. When the matter itself becomes inflated to a higher volume, its energy density goes down, which is equal to adding negative energy density, which is what Alcubierre's warp drive equation says we need. And every other warp drive paper says we need, So negative energy density is something that they refer to as something that has less energy density than the vacuum. But matter is in equilibrium with the vacuum. So if I'm creating inflated matter that has a lower energy density, it's the same thing. It is negative energy density. But now I've got an engineerable defined term of what it is and how it works. It's not just some airy-fairy exotic matter that doesn't exist because we don't know. I'm giving you guys the exact formula for what it is. You need to amplify it so that it's almost like heating it up. Heat is a source just like any other, but it's so many random frequencies. It's not precise. But heat causes objects to expand. Same thing. It's doing the same thing. But if you're expand matter and it inflates, the energy density goes down. So really, if you heat matter and it expands, its energy density went down. If you have a crystal and you heat a crystal, the crystal will expand and its energy density goes down because the amount of energy you put in is less than the amount of volume that goes up. So that's negative energy. That's the way it should be thought of, in my opinion, and in this model.
Very good.
For all of warp drive purposes.
For warp drive purposes. I'm going to copy this, Todd, and I'm going to put it in the chat. Okay. So that everybody can take a look at it for you. And there's two of them, guys. So give me a second. I'll change that back.
Yeah, my earlier draft of the paper had an incorrect calculation. So I took it out, put the paper back, and then I did the calculation right and published a separate paper on just the calculation. So I got it right. And it's much better result than the first one. Much more practical.
Well, yeah, you're over there using Chat GPT to talk to something, man. Like talking to a wall.
It is. Especially when you, like, I have to do this in Chat GPT sometimes without mentioning gravity. Because if I mention gravity, it's going to go down the black hole of general relativity and spit out all this stuff that I don't want and don't need. That's what I'm trying to do away with, you know?
Yeah. Well, it's so funny because it's like there's a rabbit hole to everything on the internet, right? So if I go on Google and I mention the wrong word, you say ring instead of circle, right? And then all of a sudden it's like all over the place. Like, dude, I don't want to get married again.
Yeah, right.
Oh, it's so bad. So, yeah, I do that all the time with that ping page, and I'm over there looking for something, and they haven't changed any of their stuff. So every time somebody models this, they always model it the exact same way. And I'm just looking for that little bit of difference, and it's just not there.
Yeah, and I'll mention Hal Puthoff because he started with his polarizable vacuum model about the same time that I was starting, and I came up with the same ideas, but we shared ideas, and his papers got published, mine didn't, but his ideas with the polarizable vacuum are again trying to affect space out there. It's not about matter, even though in that model it said that we have variable rulers and clocks. There's nothing quantum about it that says why, right? It's again, we have a polarizable vacuum, and everything we talk about is about the vacuum out there. But really, gravity takes place inside matter. That's where it matters, is in the matter itself. Is the field intersecting the matter is what makes it go, is what makes it move. We don't care about telling space-time how to curve. We want to tell matter how to move. And that's the trick. And once you understand that in order to make matter move, all we need is damping, we're golden. We just need to come up with a way to do it. Now engineers know what to do. Do it. Find a way. There's brighter minds than me out there who know all about this stuff. And all you got to do is see the equivalence, that what you see as geometry, and to put it simply, in Einstein's general relativity, you have G mu nu on the left-hand side, and you have T mu nu times kappa on the right-hand side. And we say that G mu nu is the geometry of space-time, and T mu nu is the stuff that's causing that geometry. What you should say is T mu nu is the stuff, and G mu nu is what you measure with that stuff.
Okay.
Okay, so that it takes the geometry out of space-time and gives it to the rulers and clocks. G mu nu, the geometry that you measure, is measured that way because of the rulers and clocks that change on the right-hand side, not because space and time are curved. So you have to think of it, instead of space-time isn't an object, the rulers and clocks are the object. The space-time is what you measure, is the measurement. It's the data.
Yeah, space-time doesn't change. Like, so if it's set, they don't have a force great enough to change it. So you would have to change the other force, is what you're saying, right? The one you can control.
No, what I'm saying is that it's an interpretation. It's two sides of the same coin. You can look at it as the stuff is there and rulers and clocks are fixed. Wherever you bring them, they're always the same. But the geometry changes. Or you can say that space and time has no geometry. It's just a stage. But it appears to have geometry because our rulers and clocks change depending on where we bring them.
I don't know that I buy that at all.
It's a reciprocal relationship. Here's another.
It doesn't sound right, Todd.
It's looking at it from the other side of the coin.
The space is pretty much set the way it is. We're not changing it,
It's
but
empty.
I would understand changing the clocks. And
wait a minute. See, you're giving space and identity other than empty. There's nothing there. If you have nothing,
I'm not giving it to the space. I'm giving it to the planets and things that inhabit it.
Right. Those things now, if you want to measure space using those things, what are you using? You're using rulers and clocks, or rulers, to measure your space.
Yeah, I didn't say I had a problem with that. I think the rulers and clocks change. That's all. But I didn't think it reversed. Okay, that's.
It's just here's another one. I mean, we look at dark energy as the universe is expanding and accelerating, right?
Okay.
What if it's not the universe that's expanding and accelerating? What if it's us that's shrinking? The equation that gives us the Friedman, Robinson, Walker, Lamarty equation that gives us that expanding universe, you could take the reciprocal of it. It's just reciprocity. It's the universe isn't expanding. Our meter stick is getting shorter by 6.8 nanometers every 100 years. And so as we look back in time, where things weren't contracted that much yet, it looks like they're stretching and moving away from us. But it's us that's shrinking. As energy runs down, entropy increases, and the galaxy runs down, we keep getting smaller. And the universe just keeps scaling that way forever.
Gotcha. I guess that's one way to look at it. I guess it's a matter of perspective, huh?
Exactly. And what I want to do with this paper is change the perspective of how we look at gravity so that we can engineer it instead of, engineer it with materials instead of wondering how to change space-time.
So I got to ask you while you're here, Todd. We get energy that's colder, okay? And every time I see your comment that you don't believe in the cold energy. So is it true you don't believe? Or
I know what 0 point energy is. It doesn't get any colder than that. So what is cold energy? 0 point energy is free energy, but matter is in equilibrium with it. So if you want to extract it, you need matter that's not in equilibrium with it. Well, what is that? That is matter that has been brought uphill to a higher energy 0 point with less damping, and we collect that energy by letting it fall back down. So essentially, it's the sunlight lifts water against the force of gravity, thereby storing 0 point energy, and hydroelectric waterfalls give it back, and we extract the energy. So really, if you believe gravity has anything to do with 0-point energy, then hydroelectric power is extracting 0-point energy.
I don't know,
It's taking the energy from the sun that was necessary to carry it uphill.
No, I get what you're saying. It transfers into a gas, and the gas goes up and comes back down. But then
once it's up there, the energy is stored there because it's a different damping factor. It's a different 0 point. And then it falls back down to the lower 0 point. We collect it.
Okay. I think of it, cold energy, in a much different way.
Well, what do you think of as cold energy, so I can understand that? Because I don't know what this is. It's not a term I've ever learned in school.
So basically, when you pull negative energy out of a system, it's not hot. It's cold, and it produces on the surface is cold. So when you touch it, it's cold. So when you have hot energy, right, it's like an explosive. And then when you have cold energy, it's an implosive. So it's not the same thing. It's like the opposite end of the spectrum. So if you had energy that's expanding out from the Tesla coil, right, and it's pushing out, you feel that it's heat. So the more you turned it up, the hotter you get, right? Well, there's got to be an opposite side to that. And what I'm finding is, as I put that little wire down that Tesla coil, it's colder. So in getting that to amplify, it gets colder and colder and colder. Now, the difference in the energy is you can actually touch it without getting zapped, okay? And it's still got a lot of the energy in it, okay? So
Sounds like you're talking about negative resistance. Because negative resistance is like in a resistor, a regular resistor. If you put current through it or put voltage across it, it's going to dissipate power and get hot. If you have a negative resistor, it's going to output power and get cold. This is what a solar panel does. If I have two solar panels in the sun,
okay,
and they're baking in the sun, and they get up to some hot temperature, if I now connect the load to one of those solar panels so current can flow through it, the solar panel that's providing power to the load gets colder. You can see it. That's how when we do aerial scans of a solar field, that you can tell which solar panels are working and which solar panels aren't, because the ones that aren't working glow hot or red on the thermal scan. They're hot. So if you have a negative resistance, like a solar panel, because it takes energy from the sun and then gives you power, you're not putting power into it with resistance, with current, the current's coming out of it. It tends to decrease the thermal energy of the electrons, which lowers the temperature of the solar cells, because the energy is flowing away. And so that's kind of what it sounds like to me, is that the energy is flowing away from your wire or whatever, which then cools it off.
Okay. Yeah. So we're not losing any energy, but when we pull it, okay, like you said, it comes out cold. And the thing is we can affect the system to get it colder and colder. And the colder you get, the higher the energy pull.
I would suggest do an experiment and demonstrate it.
Okay.
Get a little thermal scanner and demonstrate it, because that's very interesting if it's true. I mean, I've never seen that on a Tesla coil before or anything like that. I mean, I've got data out up the cabinets for solar fields that can show you, where the panels are hot and where the panels are cold, and say, well, that string of hot ones isn't working.
Okay. So if I bring you an experiment that shows it, you'll take a look at it?
Yeah, sure.
Awesome. You know what? I just want to see, because if we're right, then that basically means that we can take a safer energy and get to those levels that you need to get to. You know what I mean? And
that
then
works, but yeah.
then we can get where we want, because I don't think heat's the way it's going to get there. It's wasting the energy.
Yeah, I agree. It's total wasting the energy. Anyway, man, I got to go. I'm being summoned for dinner.
All right, Todd. I want to thank you for coming in today. I really do appreciate it in this discussion.
Hey, Nathan, thank you for having me. And, I'm available. My email is tdesiato, TDESIATO, @warpdrivetech.com. All right.
I know.
All right, man. Take care.
You too. Thanks, Todd.
Bye-bye.
All right, guys, give me 1 second. I'm going to pull up Todd's email real quick so I can put it in the chat. All right, and here we go. There we are. All right. Okay. So I just thought that was really cool, guys. We got to talk to Todd, and I think, you know what I mean? Look at the system, Gerald. I think that's really awesome, and I think that's kind of what we wanted to look at. And I love some of the things he's talking about. It's fascinating that you give them a perspective of how to do something so they can calculate in the correct direction, and then, like us, he's able to shift and kind of go on the page of whatever's working. You know what I mean? I think that's absolutely awesome. I like the fact that he does work with people that actually do some experiments. So that's really cool. That's something that we're real big on this channel as well. So I'd love to see some of those experiments when they put them out. I think that's really cool. So yeah, I think this is really cool, guys. And I appreciate everybody for showing up today. And, I'm sorry I didn't put up a whole lot of the chat. I just want to keep it. He wanted to get out his paper, and I wanted to give him the opportunity to do so. And I'm pretty happy that he got it out. So anyway, guys, thank you very much for coming and hanging out with me today and doing this. And thank you for Todd for showing up and talking about your paper and explaining it all. I really do appreciate it. Thank you, guys. Have a great night.